Yes. Oh, I have to click it so. And so new stick. I have the new stick. So I'll try to do it this way. So I will, for the people here, I will use the stick, and for the people online, they just have to guess where I am on the screen. So I hope you can do it. I don't have too many plots on one slide, so it should be fine. So the topic for what I was invited for to give this HIT seminar was hypernuclei and heavy ion collisions. And when I got this invitation, I had to actually think again, because I did this probably before I came to Berkeley the last time, as opposed to it was before 2012. And then I had to remember what we did at that time, and then I started doing new things. So hopefully today it's just a little summary of the things we did then, and a few new things which I hope can be interesting. And some of those things came from also discussions with Volodya, Benjamin Dönikus, and Markus Bleicher, who did a few things also on this recently. And yes, so I'll just get started. And if you don't see me, don't hear me, please make a sound or just ask. The microphone should be turned on, and the speaker should also be turned on. So I think hopefully this works out. So now it doesn't move. Okay, that's already good. Okay, I have to click. I don't know. Okay, so just for those who don't know what a hypernucleus is, just very quick reminder. Hypernuclei are basically nuclei with at least one bound hyperon. So that's pretty simple. So you probably should know what a nucleus is. And then you just imagine, instead of having only protons and neutrons, you add at least one hyperon, and then you have a hypernucleus. And they were discovered quite some time ago, I think in the 50s or 60s, I think 50s, it was 1950s. And they, from what they call Danish and Nevsky, probably pronouncing it wrong, and they got a really nice postcard here with a stamp with the event. And so actually there's a little bit of a larger version of this event on the left-hand side. And what you see here is this big star. This is where basically you have from the top, you have some kind of cosmic ray coming in, and then it produces a hypernucleus, and this hypernucleus then moves to the south of this thing, then decays, and then it was discovered as some interesting object. And well, from there on, actually, people started measuring these things and doing emulsion experiments to figuring out whether these are, or how deeply these are bound. And this is just this old, already 10-year-old summary slide on the binding energy of light hypernuclei. So they basically have atomic masses up to, at least in this plot, up to 15, and the black dots are the red dots are the experimental measurements, and the black dots are just some model calculations on the binding energy of these hypernuclei. And you can see, of course, as expected, as you increase the atomic mass, they get more and more deeply bound, and that's basically that. And of course, then people started doing even more fancy things. So they actually did hypernuclei spectroscopy, where they could look at the different shells of the hypernuclei from S, P, D, all up to H shell, and they could basically then find the binding energy in these particular shells. So you can do a lot of things with that, but that's not what I'm going to talk about today. But I just want to give you this short summary on what actually exists. So by 1990, again, this is already some time ago. Nowadays, they have more and newer stuff. But what people then were interested in is making some kind of chart of hypernuclei, same as the chart of normal nuclei. And so these would be just normal nuclei, like we have here the small ones up to, I cannot even read it on here, bismuth, it's hard to see. And these are those hypernuclei where you only add one lambda hyperon to the nucleus, right? So these are the easiest to produce and easiest to measure. And then you saw that these things actually exist. This was in 1990, and of course, after that they came even more. Of course, now you can think, well, why only add lambda? Why, if I could also add others, I could just add, for example, a cascade of psi, which is doubly strange hadron. And this was also first seen in 1959. And basically, for example, here's a little list of those which were known by, I think, also 10 years back. So, for example, we can have helium-8, what is it? Interesting mass number, and from helium to aluminium, and you just basically add one cascade to the thing, to the mix, and then you can measure again the binding energy for the, because you have two different isospin states for the cascade, the minus and the cascade 0. You can measure the binding energies, and you see there's actually a lot of structure in this thing. So there's some isospin dependence.
Yeah, what is that binding energy? I mean, is that 8 HE or HB 8B
What?
in the table? The
Yes.
first entry is 8 HE. You mean HB? 8.
No, I think it's really helium-8.
That's helium.
Really?
Yeah. So it's.
But then the binding energy that you've got in that third bullet is 8B with binding energy of 8.1 plus.
Not B, 8.
Oh, that's probably.
And with no unit, so.
That's probably better. That makes more sense. Your table must have a typo.
Oh.
Beryllium-8 is probably better than helium-8.
Yeah, probably it is.
But then
I would
right
have to check
underneath
it. Yeah,
that,
yeah.
11
I'm not. No, actually, I'm not sure, because if you add a negative cascade to right. So I mean, the name of the whole thing is given by the charge. So if you kind of add one negatively charged baryon, you can
okay.
add a proton without changing. Right?
Yeah,
So,
okay.
so you can add a lot of mass number to it without having a big charge. So I would have to check it out, or I'm not fully certain of.
Well, I wanted to ask also a little bit about this, because you keep talking about some of your lambdas, hyperons,
Yeah.
It's one way to do it. And this is maybe the most general way, but you could also add kaons, right? They carry in the strangeness, but no baryon. And people have even done something like K minus K plus scattering. Then you add
Yeah.
two strangeness units in one go. But do you know if this is bad? But maybe we have too much energy, because
I mean,
you have to absorb these kaons.
But usually one uses the kaons then to exchange the strangeness of the kaon with some nucleon, which then becomes a hyperon.
Yeah, no, inside
So,
the nucleus, but
inside-
what yeah. But if you absorb the kaon into the nucleus, maybe it's too
Would it-
much excitation or something.
I don't know if this would be bound. It's like adding
That's
an
what I-
ion to the
That's
nucleon,
what,
right?
that's what I am saying.
I don't think the lifetime would be also quite short, right?
But I thought these are made by K.
Yeah, but then the kaon exchanges the strangeness.
Yeah,
of
right.
it, right? And then you still have a hypernucleus, but
And a pion goes out.
it means that if you just can
So it's
add
not
the
really a
bind
lambda,
the
it's
kaon.
not really a lambda, you don't
Yeah.
have a lambda being like this.
Right. I mean, that's one way of doing it. I will discuss mostly the heavy ion way of doing it. Okay, so besides that, well, it seems like, yeah, okay. Again, if you add more than one lambda to the system, of course, you can make multi-strange nuclei. And then, of course, the binding energy, so if you do some calculation from a mean field calculation, you can calculate the binding energy per baryon for the number of lambdas you add for different nuclei. And then you can get basically also all kind of structure, and you could get some magic numbers if you want, but this is again quite dependent on what model you use, I would think, and needs to be measured. And just to give you a short summary, so what people have basically found is that if you think about this in terms of nuclear interactions, then the nucleon lambda is attractive, which means, and then they found that the optical potential of the lambda in the nucleus is about 30 MeV deep at saturation density. The nucleon sigma, right? You can have, instead of a lambda, you can have sigma, but the nucleon sigma is usually not bound directly from their nuclear potential, but by some isospin forces. So might be that the sigma, that's the reason why you don't find many sigma hypernuclei.
What do you mean isospin forces?
That's a good question. Holy charge. I mean, if you add a sigma minus,
Okay.
Nucleon sigma is attractive, but that's a bit of a question. I mean, otherwise it wouldn't be bound. binding energies. Here it says -28. I think there's some updates on this. Not so clear. It's, at least less deeply bound than the lambda. And lambda is attractive, and we don't know much about it, really. And anything else, let's say lambda cascade or cascade, we don't have any experimental results on that. There's attempts on doing lattice calculations for this, but it's difficult because you're looking at very large and very weakly bound systems if they are bound. But there's a lot of experimental programs. Well, I don't want to tell. There's probably more than here. And what I'm going to talk about is possible signals from heavy ion collisions at FAIR and at the LHC. So just want to mention one thing because it comes up a lot as a big puzzle, and I'm puzzled why it's a big puzzle. So if you think about how to measure this thing, these guys, they have a lifetime, and the lifetime really depends a lot on the final state interaction of this whole thing. So if a hyperon decays, it decays then, if it's in the nucleus, inside this nucleus by the weak interaction. So you have your lambda, which then decays into nucleon, mostly a pion. So now, what was observed is that as you see here, the lifetime of the hypernucleus for very different experiments is usually close to that of a free lambda and systematically a little bit low. So how to understand that? Right. So how do we understand that it's lower? Normally you would think, well, if it's bound, then you need energy to actually make it unbound, and so you would expect a longer lifetime in a very naive first attempt, right? But the hypertriton, for example, if you look at this, where most of these lifetimes are measured, which is just a 3-nucleon system, 2-nucleon plus lambda system, is often considered as a bound state of a neutron core with a lambda bound by less than 1 MeV.
Sorry, what are the A through F? What are those measurements? Are those from?
These are older. I think these are really emulsion experiments.
Okay, because they tend to be a little longer, but bigger error bars.
So the first ones are a bit older. They are from basically last century experiments, I would say.
Okay, thanks.
Right. So, and if you look at the final state of this thing, this basically then consists of 3 nucleons and a pion. But this can take several forms. For example, you can have the hypertriton decay to a free proton, free neutron, and another free nucleon plus a pion, depending whether it's pi plus or pi minus. Or you can get a triton plus pion, or you can get a helium-3 plus pion, or you can get a deuteron plus a nucleon plus a pion. And depending on which channel you look at, the binding energy of that channel is either larger or smaller than the original. And that so basically, each has a different binding energy and also a different final state interaction with the pion. So you really have to solve this 4-body problem very accurately and very precisely. And that's why this modeling of the whole thing is complicated. And people are still working on this. So just a few months ago, I saw the recent paper where they calculated the improved next to leading order calculation of trying to solve this decay. But that's basically why. But it seems like the experiments hint to a smaller lifetime, which means that decays where for example, where you decay into a helium or triton are kind of very important because they have a larger binding energy. So you gain energy by the decay. Therefore, the lifetime can be shorter.
It seems that only the heavy ion experiments are low. The other experiment not measured too, right?
This is the free one, right?
Yeah, that's right.
Magenta one is the
But
free
if you
one.
look at the other,
Yeah, the other ones, okay, yeah, these are lower and these are probably have higher error bars.
it looks like all the heavy ion experiments is systematic. So
But the heavy ion experiments have smaller error bars.
Yeah.
That's also one.
This is why it was called puzzle.
Benjamin is there. Well,
Yes.
Well, suddenly a miracle appeared and Benjamin was there and Benjamin pushed the value to the old number, but he never really explained why. We lost the
Doesn't have
beautiful
to explain
puzzle.
why. No, it's fine. He doesn't have. He just has to make the measurement. Okay, so coming
Hey,
from
there's
that,
my picture, give credit.
which picture? No, yeah.
One stolen by CERN.
He's talking about the middle one, but he claimed it. It was your idea, but you didn't make the picture, right?
I made the picture on the computer with
He could have, yes.
Or maybe he could, I don't know.
Okay.
It's not an artificial picture, it's a calculation.
Yes, but I'm pretty sure you stretched
Should
it.
give him virtual credits.
NFT. And sell it as an anyway. So what I'm
You have
talking,
no idea about the Tyrrell effect. We took the Tyrrell effect, so we rotate the nuclei.
okay.
Mechanics 1 in Frankfurt. You probably didn't go to a real university, Jan.
No, I had a terrible professor in mechanics. Just to make sure. Okay, so switching to the main point of the talk is hypernuclei production mechanism in heavy ion collisions. And why is that interesting? Well, basically because the fireball in heavy ion collisions is a very abundant source of strangeness, so you can produce any kind of strange or multi-strange objects. And then you can have, of course, it's very dense, so hot and dense in the center, and then there obviously no nuclei exist there. But once the system is diluting more, you can form clusters at or after this hadronic freeze out. So that means you have a big discovery potential, but very short lifetime, fast expansion, and finite size emission that make things rather complicated, but still interesting. So let's first discuss a little bit how they are produced. So there's basically two mechanisms I'm going to talk about. One, both of them have in common that they are the nuclei which are produced are weakly bound compared to the momentum transfer, which is happening during the collision on average. So that means they really have to be formed, or the ones you are measuring, they are formed after the last scattering in the system. There's no way around that, right? And this is true for all models. So I have not seen any model where the nucleus, I mean, even the one from Dima and Volker, once you scatter your thing on a pion, it's destroyed, right? So there's no way around that. So this is true for all models. The observed final state must be formed after the last scattering of their constituents. That's just has to happen. The point is how to do that. And in this talk, I'm going to give you two mechanisms. One is the absorption in a warm nucleus. So what does that mean? That means that hyperons, which are produced in the hot collision zones, they can have very large longitudinal momentum, which means these can be absorbed at a later time in the spectator fragments. So in your heavy ion collisions, you never have a fully central collision. You sometimes have peripheral collision. These peripheral spectators, they are rather highly excited nuclei. They will fragment later on because you cut basically out half of it, and then it's highly deformed and has a high excitation. It will fragment. But if at some later time, by chance, you have a hyperon nearby, this thing can get reabsorbed in the fragments. And then these hyperfragments, or actually you produce a hyperfragment, and this hyperfragment then decays according to certain fragmentation rules. And or you can just have cluster formation after the freeze out from the fireball, so where it's really hot. And there you can have hypernuclei or small hypernuclei, which can be formed after the kinetic freeze out and after all interactions have ceased. And this is usually the calculation on how these clusters are produced or formed, or how many of them are formed, is done by using a coalescence mechanism, which I will be describing soon. And there's different versions of implementation, but mostly similar results on most of them.
Sorry, but what is a kinetic freeze out?
So kinetic freeze out means that last scattering of particles. So at the point where the momentum distributions of the particles doesn't change anymore.
You have different kinds of freeze out. people also talk about chemical.
didn't want to-
right? That's when the species don't change it, but they can still collide.
Yes.
Right? So this kinetic comes later when they stop colliding. Right?
Okay, so first thing I want to talk about is this, what we did about 10 years, more than 10 years ago. And that is basically absorption in warm nuclear matter, what I mentioned before. So you have, this is what I show on the right-hand side, is a little bit of a few time frames of such a collision. So you have one nucleus coming from the right, one from the left. They have a little bit offset along the x-axis, along the beam axis, and then here in the middle you see them colliding. They're very squeezed here because they're Lorentz contracted. And then there's these red dots, which are hard to see on the screen here, but on the other screen should be visible. And this is basically where my lambdas are produced, hyperons are produced, right? And outside of these green bands, you have the spectators, those which don't do anything. So now if we wait a little bit, you can see how lambdas still can be produced during the course of the evolution, but also you can see how then at later time, they kind of travel outwards into the direction of the spectators and how they can be absorbed.
Energy is that?
I think this did at that time. Question.
Why is the heat buff in the middle? That's my question.
This is
What do you
either low energy or in very fine. Oh,
Lorentz contractions are not so big. Right?
Yeah, I think this was SPS and then something like top original top fair energy, which was 40 or something at that time.
But then the Lorentz contractions.
What are the numbers on the right? These are the lambda.
This is just a number of collisions.
But what
Or
is it
number
that-
of generated
What is
lambda.
it that's plotted?
No, the answer one.
So they're spread out like that because of the
This is
the
this is
impact
much longer
parameter.
time. These are basically time frames, right? The first one is from 0 to 7, second one 7, and the last one is from 35 to 70 Fermi. So that's all lambda interactions in that time frame. So that's why it's so wide.
Yeah, but why-
Okay, but these are lambda multiplicities.
Like each point is an interaction. Basically.
Yes, but the number is at n lambda equals 300 something. That's the lambda multiplicity in these different collision
Right.
regions.
These different regions, yes.
Okay, thank you.
It is of course not of one event, but this is over.
Yeah, over time.
So this is just giving you a relative idea of relative lambda interactions in these different regions.
Okay.
So this goes to my question, what is it that is plotted?
So each point is, well, these are different collisions. So you basically have pyronucleon making a lambda, or anti-kaon nucleon making a lambda, or nucleon making a
This
lambda.
is where the lambda is made.
This is basically where the lambda is made, yes. Or well, not made, all right. So here you have hyperon nucleon going to hypernucleon. So this is basically just, could also be elastic scatterings. So this is where the lambda is at a certain time, and you can basically see at late time it sits where also the spectators are. Or it can be.
Which panel is the kinetic freeze out?
Well, kinetic freeze out happens is in this case is not so relevant because I'm looking at stuff which is happening at very large longitudinal momenta, and kinetic freeze out is something which is more or less relevant for the second mechanism, which is formation from the hot fireball, which is here in the center. Right? So this is where if I would be interested in hypernuclei formation from this very hot zone, I would look here in the center, and then kinetic freeze out. Time-wise, kinetic freeze out in the center usually happens about after 20 or 30 Fermi over C. So maybe this one, but for this absorption, it's not so relevant because they have a very large velocity, so they different frame is in the center.
So there is stuff in the center. There are just no reactions left anymore.
Exactly. That's that's basically what you see. Nothing much happening here.
But there are particles flying.
They are flying out,
but
but
they just result.
Yeah.
So the reason for the stretching in the lowest figure is simply that you start at 30 and you finish at 70. It has nothing to do with a momentarily
Well, that's
stretched image. It's just beep, 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 every Fermi, one guy, and that over 35 Fermis.
Yes, exactly.
Why is there nothing left in the middle?
I thought it's slow and stretch.
Why there's not?
Not
Well,
Lawrence,
because it's
but just a consecutive emission, because it stretches over almost 40 Fermi over
yeah,
C.
because there's
The
after
guy is 40 Fermi long, that's all. But why is nothing in the middle?
because there's nothing much happening regarding lambdas in the middle anymore after this long time,
At that time, it's gone.
right?
Yeah, I mean, if most of the production is through pi plus nucleon, then that's long gone.
This is a very recent paper. Right?
But this is from this one old paper. This new one is a different one. This is actually for lower energies. Okay. Okay. So, but like once you do this, you can just estimate how many of these hyperons are absorbed, and then you can basically let them decay. So, right. So your hyperons are produced in the collision zone. They enter the spectator region, and then they are absorbed. So you can, let's say, do the same for lambdas and cascades. Assume some nuclear potentials, and then, well, we did this with 2 different models, and they gave very similar results. And these excited fragments, they have about, well, let's say 5, 6 or 7 MeV temperature, and then you can use your multi-fragmentation model to calculate your fragment sizes and so on. And what you get is that you get mostly large hyperfragments, and that what you will see on the right-hand side. So the upper plot gives you the probability for that your fragment before it decays has a certain number of hyperons. So most of them, of course, have 1 hyperon, and you can have 2 or 3 even, at 0, 1, or 2. And at 2 GeV and at 20 GeV, of course, you can have even more because you're producing more strangeness. If your beam energy increases, you can even have 3 hyperons in this fragment. And then on the lower side of this plot, you see the residual mass of these fragments, and you see that they can be very large. So you can have mass fragments of 100 or 150 mass, which have strangeness 1 or 2, and then of course the final fragment, this will decay. Then you can kind of produce all kind of different hypernuclei from this. Okay. And actually, you could do similar things if you go to low energies. This is newer paper where basically one said we will look at all. If you go to very low beam energies, let's say 1 GeV and below, then you can say, well, I treat my whole system as a big hyperfragment because everything is stopped more or less, and then it decay this according to multi-fragmentation, and then you can also try to estimate your fragments. So this might be an interesting topic. Okay. So let's come to something. So this was more or less you have some model, you try to follow the path of your hyperons, and then you make some assumptions on whether they will be absorbed or not. But in reality, what you actually really want, if you want to describe everything properly, you want to have a dynamical model which gets everything right. So you get all your interactions. The nuclear interactions are included properly in some microscopic model throughout the whole system's evolution, and then in the end you only have to pick up what you get. Right? So you calculate everything properly. You have your full Hamiltonian of your system, which you can solve, and then you can use to solve the time evolution, and then you can just calculate the expectation value, for example, of a deuteron or of a hypertriton or whatever you have. However, this is practically almost impossible, since you basically would involve solving the proper time-dependent many-body quantum system potentially relativistically for this very complicated system that you create in heavy ion collision. So you cannot do that. There was one attempt recently, which is now called the PHQMD model. I have to mention it, but actually that follows this idea that, well, people usually do very simplified approaches. If we could include somehow the proper interactions, then we would just have to count the clusters. We don't have to produce them, but okay, this is done here. Still, this is not a full quantum mechanical approach. It's a classical model, classical molecular dynamics model. so you don't have really any quantum effects.
What does this Q then stand for?
Well, it's the Q stands for quantum, but it's, I mean, instead of using point-like particles, you use Gaussian wave packages. That's the whole trick. Right? So that's,
Comes from from the first author.
well, it's both. Yeah, this comes from Jörg, and the first two letters come from again, so you don't have any spin. There's no wave functions really. I mean, there's Gaussian wave package. There's no anti-symmetrization effects or something like this. It's non-relativistic mainly, except for some gamma factor somewhere in the density calculations. It requires a lot of fine-tuning if you want to get out simple nuclei. And it still poses the challenge that even then, if you calculate all this thing, how to find and identify now these bound states if you're not solving the proper quantum mechanics. Right? So you just have some clusters, and you have to apply some clustering algorithm, and then you have to throw away 90% of those, and so on and so on. Okay, so what people actually do, instead of trying to solve the full problem, is they do something which is called phase-space coalescence. I call it a practical implementation. And what is done in very general terms in phase-space coalescence, you take a transport model of your choice to calculate the phase-space distributions of baryons as function of time and after kinetic freeze-out. Right? And once you have that, right, so you have your FA and FB, which are these distributions of your baryons. Then you just assume some cluster is formed whenever the correct combination of baryons occupies a certain phase space volume defined by this rho. Is it there? Yeah, so this is just some function which depends on the coordinate and momentum space difference of these two baryons. Let's say this is a 2-baryon state. But if you have a 3-baryon state, you add another FC and you have another function rho. Now I try to put few of those references in here. So this is the people have been trying to do this for some time, and there's a lot of publications on this. So I'm not going to go through all of this, but I just want to mention it. But there should be a little bit of discussion how to interpret this rho. So this density rho, this is often just interpreted as wave function of this nucleus which you want to describe. And this is assuming that it only has positive probability, but it's not necessarily true. For neutron, you can say this is true, but okay. To get the more complicated nucleus, it might not always be a positive, so but you need this thing to be always good. Of course, this interpretation is strictly only true if the neutron is essentially formed and FA and FB correspond to interacting nucleons. So, or we assume that only nuclear forces are acting, nothing else, and no other hadrons, no other interactions. This is a completely isolated quantum system. Then this interpretation is probably fine. Problem is that in practice, FA and FB are evaluated before nuclei could form and for free nucleons which don't interact, or which have not interacted according to nuclear forces before this method is applied, just basically as scatterings cease. So that makes it a little bit more difficult, and this is very problematic, especially for large nuclei, as we will see later. And this, I would argue, this leaves some room for the implementation of this rho and the interpretation of this rho as probability density and not necessarily the wave function. But okay, we could come to that discussion later if you want. So what I'm talking about is I'm just going to tell you what the specific model I'm going to use to calculate my distribution. That's going to be the UrQMD model, which is basically a microscopic transport model. Why? Well, coalescence needs some realistic distributions for hadrons as input. So I don't want to just take anything. So I just need a model for this, and I take a model I know. So we will, for the following, we will use UrQMD in 2 modes. One is the cascade mode, where you just basically the whole model is described as hadrons which scatter elastically and inelastically, form resonance, a string, and so on. But however, there's no additional nuclear forces, no long-range interactions, and so on. And we will use a hybrid version of this, which has, that would be this. So you have your UrQMD, you run it until a certain point, and then you can either run the full evolution within your microscopic transport model, or you can switch to some fluid dynamical model, which describes your dense system evolution. And usually this works very well for higher beam energies. And then, but both models allow us to generate event-wise distribution of baryons at large scattering, and that's the important thing. So for each event, we can have this distribution. We can look at their distance in space, distance, momentum, and then we can basically perform our coalescence analysis. And just to go once through this numerical procedure, which I call box coalescence, is very simple. So basically, you do your simulations. Then as a first step, we look into the two-particle rest frame of each. Let's say this is for the deuteron. For each possible two-nucleon pair with the correct isospin combination. For example, if you want to do a deuteron, you need a proton and a neutron. And I will come to the hypertriton in a second for deuteron. And if you want to do a triton, for example, you just look at proton, neutron, neutron triples. So if their relative distance is smaller than some parameter, which in this case for the deuteron would be this number, and if the momentum of these in this frame is less than another parameter, which is again more or less 3 parameters, then a two-nucleon state is potentially formed, and you can calculate the combined momentum and the position of this whole thing.
Is it done at equal time for the pair, or what's
Yes, so basically you go to the center of mass frame, then you propagate the particle with the earlier time to the later time, and then you check for distance and equal pairs.
So you said quite correctly, to make a deuteron, you need isospin 0.
Right.
But you also need spin 1 to calculate
Right.
spins of
Yeah.
the 2.
Yeah.
You just put in a factor quarter or something.
Yes, so yeah, that's the last one. So the way it's done is, yeah, that's fine. So, but first let me finish the second step. So that would be now getting
Jan,
out.
before you keep on going, how can you possibly have 4 digits, significant digits?
Yeah, that's actually a good question. Absolutely. Yes, exactly. Well, I probably would say there is quite some room for this to be not 7.5, but 8 or 7 is also fine. I agree. This should all not be a 3-digit number. Totally agree. But actually, this is from a paper I didn't write, so that's okay. So I just took these values, but I guess from 3, 5, 7 will give you the same result. So once you have your deuteron, what you do is you then boost it to the local rest frame of this 2-nucleon state, and then another possible 3rd nucleon, and then you do the whole thing again, and you have a new set of parameters, and then you give this thing. So if you fulfill all these parameters, then again you have some kind of formation probability, and then that's where the spin combinations come into play. But it's also that depends on what. When you have a deuteron, it's 3/8 because it's not just spin, but it's also some asymmetric combinations of the wave. There are papers written about this. I never understood them. We just use it. Then you have
Read Remler.
Huh?
Remler will teach you how to not understand papers.
Yeah, that's right. I don't think I think it was one of those guys who wrote this. And everybody is using the 3/8 instead of using the 3/4. Okay. Again, then you can calculate the momentum and the position, and that's it. So you have that. And if there's no 3rd particle found, the charge equals to 1, then you have deuteron. Again, with this 3/8 times 1/2. No, it's actually 3/4 times 1/2. Depending on whether you actually choose proton or neutron or not. Okay, so that's how it's done, and then you can basically do this for any 3-particle state. So instead of having a proton, neutron, neutron, you can have proton, neutron, lambda. Yeah.
But the numbers, like the 4 digits on that.
Yeah.
You said these guys are mostly parameters that you fit.
Right.
So depending on what you input, you can easily go to 4 digits.
Yeah, I could put in an 8-digit number if I want. Horst was just complaining that the data are not on a level that we can actually fix it to this accuracy. Right. So how to fix these parameters, I will show you in a second. But what always comes up in here a lot is that, you know, coalescence is just only allows you to calculate ratios and so on, and you have to look at the underlying distributions, how they were generated, whether there's some systematics in there, and I fully agree. So that's why I show you first the underlying multiplicity at mid-rapidity for protons, lambdas, and sigmas, and cascades from the models I use. So you can later complain how useless they are and how wrong. Exactly. So Volker is already looking at the right things. So basically, overall, I would say it's a more or less reasonable description. So the black points are data, and the colored lines are model calculations, and the closed symbols are the ones from UrQMD, and the open symbols are the ones when I turn on Hydro.
That's
That's where the phase transition comes.
the rest are like this community.
That's the critical point here.
Exactly. So, well, this jump happens wherever I turn it on. Why? Because in hybrid model is grand canonical strangeness production, while in the microscopic model you have microscopic strangeness production, and that's why, especially for the cascade, you get this huge difference in total production. But even if you go to protons, there's a difference which has to do with different stopping. This is really just the mid-rapidity here. So depending on how much energy is deposited or is moved out of this mid-rapidity region, you will get a different yield. And this is something to keep in mind, right? So if I use this as input for my nuclei, of course, I will also get different nuclei multiplicities.
What is the GC strategy?
Grand canonical.
Grand.
Right? I mean, I could use right, but if you do a thermal model without thermal escape, you also get too much.
So, Jan, since you said you never understood the fact that the 3/8, can I try
Oh,
to
please.
get- I mean, so you have two nucleons, right? The
Yes.
question is, what's the chance they form? The two
Right.
things, spin, isospin.
Right.
So the isospin first. Isospin means they have to be different.
Right.
So they are either similar or they're different, 50-50.
Right.
That's a factor half.
Yeah, but that is already
And then there's the spin, either triplet or singlet, right? Triplet or singlet, 3/4, 1/4. So it's 3/4 and a half,
Right.
3/8.
that's right. The problem is that people always use 3/8 and the half. That's what I don't. That's all.
That's maybe a little bit double, I think. Yeah, so this I don't understand.
No, actually, but there are actually papers about
It has to be,
that
okay.
it has to
So,
be
okay, so that's
one
what
half.
you meant. There's some extra factor half there somewhere.
That's but that factor half is always
So
missed.
why, with the isospin, why does it have to be 1/2? You have four.
Yeah, so that's a 50% chance they're the same or 50% chance they're different.
No, but isospin is the same as spin. You have the
No, so I just been you're in a triplet or in a singlet.
Because you're fixing neutron proton. This is the neutron. You're not saying neutron proton.
But you are actually, you have a good point, because the neutron is an isospin singlet, right? So that's just the one of 25% chance.
So it's
You
quarter.
can have them,
It's actually
be
three.
neutron and proton, but still be in the isospin triplet states, what you're saying.
Yes.
So you are right, so it's 1/4 time, so 3/4 comes 3/16, this is.
Maybe
they
that's what
use.
it is. Yes.
So you're. Perfect.
Yes.
Perfect.
Good.
That's
Okay.
right. But then it's wrong to say 3/8 times a half, that doesn't make any
That's
sense, right?
Well,
It's
depending.
3/4 times 1/4, that's exactly what you're right.
Depending on how you select your nuclei, because the one anyway. Okay. 3/2, 3/4. That's the thing. No, 3/8. So. Okay, so doing this, before we come to the hypernuclei, we can look at the light nuclei multiplicities, basically neutron, triton, and 3. And again,
Where's the triton? I don't see.
the triton is the green one below the blue one, and you can see already that the difference between triton and helium-3 are very small, and they are only visible at very low beam energies, where the total isospin mid-rapidity is not 0, and in high energies, you're basically isospin at mid-rapidity goes to 0 because it's not stopped. This is, of course, assuming the same parameters for triton and helium-3. If I choose different parameters for it, I could get different multiplicity. Again, comparing to data, you already see, well, it's a log plot over many orders of magnitude, so obviously everything looks the same. But there are differences, so this is basically star data here. Seems like we're overestimating a bit. If we go to the highest energy, where at the LHC, where Alice data is, we're underestimating a little bit. And so that's basically what you get. So this is probably a result of too much stopping. And as I said already before, you already see this in the protons. You have a little bit too many protons, which translates in too many nuclei. And then you can take a special double ratio of these. Again, this is all still not strange, but it's still interesting. And this double ratio is quite interesting. So you take the number of tritons times protons over deuterons squared. And of course, now you can plot this on a linear scale, which gives you a little bit more power to distinguish stuff. But also you kind of cancel out a lot of effects of the total number of baryons, because right, you have 3 baryons in here, 1 here, but 2 times 2 in the deuteron. And again, so the black line here is our calculation from the UrQMD model. The orange one is from the hydro model. So there, again, there's no big difference. And you see all these data, right? So you have star data, NA49 data down here. You have Alice data up here. And then you have Phoebe data down here. And you can see there's a lot of stuff going on. This increase at low energies is quite interesting, because this is due to the fact that at very low energies, the probability to produce large nuclei is very high, because you have a lot of baryons stopped in the center. And that means the more tritons I produce, the less I have left for deuterons. So that means if I take this ratio, then this actually goes up. However, the data show that they are flat. So this is kind of interesting.
So how does the Heidelberg government explain this apparent total failure of thermal model?
Yeah, that's Volodya says the data is wrong.
The data must be wrong.
So far away.
No. Volodya says the government says the data are correct.
The government approved the data.
Yeah, I mean, in the thermal model, since you take this ratio, you mainly see the temperature dependence here, right? I mean, this little step here is from the temperature dependence, and then temperature stays constant and then nothing happens, more or less. So I could changing my parameter, I could just move my curve up, but it still would be constant and still would be going up at low energies, simply because of the fact that more tritons means less deuterons, and so this ratio goes up. So I think there's still things to understand. So moving on to hypernuclei. Here the problem is that the data on hypertriton multiplicities are quite scarce. So there is not much to do. We have one point here, up here, this is multiplicity. So there are some other points for ratios, but not multiplicity. So we want to fix our parameters with multiplicity. So we have one at the LHC, and this one is not even fine. This is it's still preliminary star data. I'm not sure if it's published now or not. But these are these 2 points we have. And basically we have 2 parameters, but then there's more problems coming in, because you don't really want to fix this point down here, because we know at these low energies, the underlying model already overestimates hyperon production. So if you now fix your parameter with too many lambdas, then you maybe making a mistake. So we kind of said, okay, let's fix our parameters a little bit differently. Just take our delta, take this interpretation of the wave function literally, and see what happens. So we take our delta R max to be 9.5 Fermi, which is roughly the size of the hypertriton, which is a huge object compared to the whole system. And then we just have one parameter, and we fit it so that it reasonably reproduces old calculations, which were done here again with some hydrodynamic model and thermal production and some other old calculation of coalescence. And then what we get is something which looks at least reasonable. Again, it underestimates results at the LHC and a little bit overestimates at 3 GeV, but that is probably due to the fact that we have too many hyperons in the system. And then, of course, once you have the hypertriton, you can look at other interesting states. So you can not only look at, as I said, there might be multi-strange objects. So you can protect those, for example, the H-dibaryon, which is a state of two lambdas, or the cascade nucleon state, which has the same quantum numbers basically, but it's different realization of this. Or you can have a state which is a cascade in two nucleons, so like a hypertriton, but a cascade triton. And then we can just take the same parameters as we did for hypertriton and calculate what we get, and then we see, well, there's quite a lot of, you would expect quite a lot of this H-dibaryon cascade, and here in the cascade is so many because we kind of summed over all possible isospin combinations. And again, you see the little jump here when you switch on the hydro and so on. So that's as expected. But this is really a large expected multiplicity, and even for the nuclear system. So if they exist, there's a very high chance that they would be observed. Again, we don't even know that these states actually are bound. That's the
So you use these large ranges also for these states?
Yep.
Is there a problem with the H-dibaryon, which I think is the upper down strange range?
Yep.
If that radius is much smaller than expected,
It drops.
depends. Well, you have two parameters, right? So I think it wouldn't change that much.
Jan, I remember that we published this result, which you just showed 10 years ago, but then the curves would dramatically fall down above 10 GeV. How come that the curves now stay almost constant and flat?
So the gray solid line and the gray dashed lines are our predictions from 10 years ago. So they basically give the same. I think it's just the plotting. Here I plot over 6 orders of magnitude.
Oh, yeah. Okay, thank you.
So basically, we kind of reproduce the old stuff pretty well.
As usual.
As usual, yes. Okay. But there's another special ratio which you can do with these hypernuclei, and that is this S, I call it S3. And that's now a ratio of hypertriton over helium-3 times proton over lambda. And again, this thing basically tries to cancel out everything which depends on the baryon number or on the exactly in all kind of prefactors and so on. And again, here we see a little bit of difference from the old calculations. So our old calculations for the hydrodynamics were basically flat. And the old calculations from this Dubna cascade model coalescence were kind of increasing, which was, as I understand now, due to some kind of weird decrease in the helium-3. But our new calculations show that they are essentially flat at low energies, then increase for some reason, which we will discuss later, in some intermediate energy ranges, then again stay flat. And if you look at the data, well, it's really hard to say anything because they have huge error bars, but I think this is quite an interesting behavior for this particular ratio. Now, let's switch to understand and maybe a little bit why this might be interesting. Let's switch to the centrality dependence or system size dependence of the whole thing. And again, as I said before, people always complain we never show the absolute yields of particles and so on. So that's what I do. So I show you here this is now collisions at the LHC, the 5 TeV, lead on lead, and proton-proton collisions. And what I show here is the pion, kaon, and proton number from our, again, hydrodynamic plus UrQMD model compared to Alice data. And what you can see is now, surprisingly, pion number more or less works very well. However, the proton number in the model is now overestimated. This is a little.
On the middle, I suppose.
No, kaons are here, protons are the lower. Yeah, you have more kaons. It's 0.
LHC is 5.
LHC, you have kaon mass is 500, proton mass is twice that. So
That's not what you had at the battle act.
exactly. Right. So, but what is surprising is that at 5 TeV now the model kind of overestimates even proton number, which if you go to the 2 TeV data of LHC, that wasn't the case. There it was actually spot on. And that's actually something I don't really fully understand why it is like this, but it's a whole different topic. Anyway, centrality dependence is more or less reasonable. We can see there's a little bit too much stopping in proton-proton, and there's probably similarly also one of the reasons why we have this behavior.
This is the total number, right? It's not net proton. It's just
This is
number.
total number, just protons. And the anti-proton number is the same, so because you have full symmetry basically. And one thing we already did a few years ago for 2 TeV is to calculate the centrality dependence of the deuteron to proton ratio. And what we observed here, this was the blue band, is that if you go to very central, so centrality here is measured the number of charged particles that goes into the detector. Right? So if you have more central collisions, you have more charged particles. So we basically, if you go to the central collisions and then go more peripheral, suddenly this ratio increases. And this is different to what, for example, you would expect from some thermal model or so, because there it would just be a flat line. And this was understood basically as a result of annihilation in the hadronic phase. So you basically have the hydrodynamics, you hadronize your particles, and then they go through some hadronic freeze-out stage. And during that freeze-out, you can annihilate protons and antiprotons. And if you do that, then the deuteron will feel this much stronger, a little bit stronger than the protons. Therefore, the ratio actually goes down. And this is again reproduced if we go to 5 TeV, that's the orange line, so that's the new results for the slightly higher energy. Again, there's a slightly overall shift, but again, the centrality dependence is quite well reproduced.
The difference between 2.7 and 5 TeV and the UrQMD hybrids, where doesn't come from? What's the mechanism?
Well, one of it that the system is a bit larger, so you might get a bit more annihilation.
Yeah, but at the same charge.
Yes.
Yeah, it's
Well,
the same
okay.
size.
Yeah, but it's a different shape a little bit. I think the main effect comes from that I use a slightly different freeze out.
Okay, so there is slightly.
So these are basically, I would call this model dependence. Also there was an update on how the deuteron coalescence works, on which order, because this also includes now tritons, and then the ordering was changed. That had a small effect. Yeah, so there's many details which can have an effect on this. But actually for me, this means, well, within the errors, it's fine. Give you the same qualitative result. So
Jan, what is the green triangles, Jan?
which green triangles? Is down here at what is here?
At 10, yeah.
That's data, that's proton lead, I think.
Okay.
So the expectation then what was for if we take the ratio of helium over proton, we would see the same behavior, that it first kind of goes up and then down. And that's what we kind of get here. It goes up and down. Overall, we underestimate a little bit. This is actually, this might be a different imagery. I have to ask Benjamin which point these are. Anyway, so we expected the same thing, but we also expected the same thing for the hypertriton. But for the hypertriton here in red, it didn't go up; it just went straight down.
This you way is that underestimate?
Yes, it's underestimated. Well, here it's underestimated.
Yeah, that's
Here, I don't know. Here, I don't know. There's,
no the red one.
but this one, oh, so the points are all, so the circles are all for helium over proton, right?
Yeah.
The red ones are for, and the squares are for hypertriton. So there's no hypertriton data
Oh, there's
except for
only
the
one
one
point. Yeah, there's
point.
one
Yeah.
point.
But that was kind of, I mean, what I thought maybe at first glance you would think, well, maybe there's an overall shift because you have less hypertritons, but the general behavior that it goes up and down should be the same. But no, it just went straight down. And oops, that's the wrong one. So this was a little bit discussed. That's why it's good that Benjamin is here in this paper. And they said, well, this can this decrease. So this is again the same ratio, hypertriton over lambda. From this calculation here is also some coalescence model, but it's not based on a microscopic coalescence, but it's more like and waving coalescence ratio. and here it was explained by the difference in the delta R. So basically, if you the size of the hypernucleus is about 9.5 Fermi, and the size of the 3 is 4.3 Fermi. Now, if you say, if you make this interpretation of this whole thing as the size of the wave function, and you go to peripheral systems, these peripheral systems will be probably smaller than 9.5 Fermi, and then it means you get a reduction of the hypertriton simply from the size. However, there is a problem, of course, and that's what was done in Volodya's paper. Again, Benjamin explains everything with everything. And you can see that basically you also should have an effect from the canonical suppression. So because in very small system, proton, you don't, in one event, it's very unlikely to have enough protons, one proton, one neutron, and one hyperon to actually produce. That's what you need. So you will have, in a very small system, that you have a canonical volume in which all this should be conserved to 0, and that will reduce the yield for very peripheral events or for very small systems.
This is no thermal production.
This is thermal production, but it just basically gives you how big would the effect of a canonical volume be, right? Of baryon charge and strangeness, for example, but this is mainly baryon charge. Right? So you cannot just produce 3 baryons from nowhere. You have to produce also the antibaryons in a small, very small volume. So that's very unlikely that in a small system, while in a large system, it's more likely that you have enough energy floating around that you can do that. The problem is that in our, the good thing in our approach, we have both taken into account because our proton-proton collisions basically have a microscopic calculation, so everything is conserved. And we also can look at the size effect. The interesting thing is, I'm almost done, is that one can understand this decrease also without making any assumption about wave functions. And that goes the following way. Let's say you have some kind of, let's simplify our freeze-out surface on which I kind of calculate all my distributions or from which I take them. So I simplify them as a big sphere, which is probably not so bad. And then I just look, okay, if my red one is, let's say, my neutron, and my orange one is my orange point here is my lambda, and then I look at my delta R. And if this delta R is much smaller than, let's say, the whole thing, the curvature is quite small, and that means that on average, the emission direction of these particles will be more or less in parallel. And if you have large flow, then this gets even more correlated. That means that R and P are more and more correlated if I have a large emission.
But delta R is 10 Fermi.
Exactly. So this is if I have a very large ball, and if I have something now where the delta R is rather similar size as the system, what you see, right, is that the preferred emission goes into maybe in a different direction. That means that R and P are much less correlated, and that means you will just get, you're less likely to get a hypertriton. Right? And to see whether this is true, what we did is we just changed our radius of the hypertriton from 9.5 to 4.3, which is the same as the helium-3. And then we also would have to increase the delta P accordingly to actually get enough hypertritons in central collisions. And now you see difference between red and the purple curve, right? So now the purple curve is if I make the hypertriton delta R smaller, and then I get the same effect. Suddenly it goes up and down. As for the helium-3, and even in very peripheral ones, I get a very similar value than for the helium-3. And that means that basically most of this effect comes from the size or the emission volume of the particle. Again, this doesn't mean that I need to interpret this as the wave function size, which I could, but I don't have to. And basically, this large spatial distance at freeze-out leads to decorrelation of momentum for small systems and thus a suppression. And well, again, this interpretation of this being uniquely connected to hypernucleus wave function is a little bit questionable, I would say, but others might have different opinions. again, I don't think that this large hypernucleus can be considered as an isolated quantum state at the last scattering, maybe at some very late time, possibly. I would go with a little bit weaker interpretation, and that is that this coalescence criterion only gives a probability that a set of baryons can form a proper final state nucleus at some later time, and then the source volume is not equal to the size of the wave function. It's the volume of the source out of which those nucleons come, which eventually form a nucleus. You can, of course, still keep that and say, well, but that's my wave function size. Still fine, but the left thing that is the source volume is still true. So this also comparison then does not serve to determine whether the above, or it does not, also it does not help to discern coalescence from statistical hydrogenation model or thermal model where you just have the input being the temperature. I would even argue that it does not even make sense to try and discriminate the two, coalescence and thermal production. Basically, there are different approaches to describe the same thing, and the thermal model does not attempt at describing how anything is produced. Neither does coalescence attempt to describe how anything is created. But they are both more or less giving you certain probabilities, or based on a phase-based distributions. Okay. Again, interestingly, just to point out, because it was also in Benjamin's paper, similar behavior is observed for the double ratios. If I take this triton times proton over neutron squared, or the S3 as function of centrality for the same system, I again get that this triton over proton over triton proton over neutron squared is more or less flat, while again this S3 drops very, very rapidly. And if I make the calculate the S3 with a smaller delta R, I get something which is more or less flat. So again, I can get both cases depending on what I choose for my delta R. And again, since we are doing TP at the very peripheral conditions here, the canonical effects are naturally already included. Okay, with that, let me conclude. So I would think that light hypernuclei nuclei can be described within the coalescence formalism very well, with only 2 parameters over 3 orders of magnitude. I mean, this is of beam energy. That's something you should keep in mind. We don't have to refit these parameters for every beam energy, but just keep them once. Maybe one should not do this, but it works more or less reasonably well. You know, heavy ion collisions are always an abundant source of multi-strange and small hypernuclei, and large ones probably too. The system size dependence of hypernuclei is influenced by the source size, which depends on centrality, but also may be influenced by the radial flow. Again, this interpretation that source size is size of the nucleon wave function, that is something what has to be argued. Again, the beam energy dependence of S3, as I showed you before, which showed this little increase, might be due to the decrease in the source size from radial flow or a larger freeze-out volume at Mitra Peninsula. This is something which we can still study. And we will do a comparison with the thermal model. So I hope Volodya will join here, and we'll get the manuscript out on this hopefully soon. So thank you very much.
Thank you. Thank you.
Very good.
Bravo.
Thank you.
My
So-
battery is low.
Quite a lot of questions from the audience here. Let me see whether there's any questions from offline.
There were some.
Any questions?
I don't particularly have a question. I just thought it was a very nice talk.
Let's go to Nung first.
Yeah, Jan, thank you for the nice talk. My question is, I actually could not get it here. From this, if we measured hypernuclei with a good precision, can we extract information about hypernuclear interactions?
You want to? Sorry.
Can we extract information about hypernuclear interaction?
Well, you want to extract something like the binding energy or so.
Oh, it's binding energy? I see.
What do you mean with hypernuclear interaction?
for example, the potential.
Yeah, finding. But doing that from heavy ion collisions is challenging because those final states they have some widths. Can you turn off? Okay. I would say I don't think heavy ion collisions are necessarily the place where you want to do high precision measurements on spectroscopy of hypernuclei. But if you have something, some new states or some multi-strange states and just want to show that they exist, that's probably where you want to go to heavy ion collision. But if you want to determine the binding energy on the level of a tenth or a hundredth of an MeV, then I don't think heavy ion collisions are necessarily the best place to do it. They're quite dirty.
Okay, thank you.
Shin?
Shin, I think.
Yeah, Jan, a very nice talk. I have actually two questions. The first one is related to Nu asked about the Y potential. You comment that measuring binding energy. This can be done also in heavy ion collisions, just measure the binding energy directly. Do you think also that's can have a more direct connection to the Y-N interaction by measuring the binding energy or lambda separation energy for different hypernuclei?
I mean, that would of course be interesting if you can do that, but I don't have. Has this been published somewhere?
Oh,
I've seen
Star has one. Yeah, Star has one on the hypertriton, and we are working on certainly other light hypernuclei as well. And yeah. Okay.
Can measure things which have not been measured before. That's of course good, but
yeah. The second question I have is you focus on the mid rapidity. Can you calculate the rapidity dependence of the hypertriton yield?
Yes, we can. For basically anything except for the highest energies, because there we have to basically then make up some initial distribution for the hydro, and our hydro does not really work at high rapidities. But I would say for anything up to maybe 20 GeV, we can look at the rapidity dependence. I mean, I just showed the mid rapidity, but in principle, I have all the other ones too. I mean, I just looked at the mid rapidity.
Okay, great, thanks.
Anyone else?
Anybody else? Well, what?
Yeah, sure.
Yeah, go ahead.
Can I look at slide 23 again? So I'm looking at the H diversion. And so my question is sort of strange because this H diversion is a dark matter candidate and it needs to freeze out at Big Bang nuclear synthesis or around then, which is like 200 MeV. So my question is, what energy are we? I'm sorry, should we able to see this? We're at 10 GeV. What energy is this plot?
Oh, okay. So the energy which is plotted here is the collision energy of the nuclei, right?
Okay.
So, but also I mean the H diversion here is basically a lambda system.
It is more a strong.
It is not necessarily a 6-quark system, right? Which might be some different thing.
It's quite different, right? The radius has to be very different.
Right. So this is a big like a nuclear state. It's not a quark state.
If I asked you before, like what happens if it goes down to the
Yeah.
radius?
But I mean, then of course the relative momentum can increase because it can squeeze it into a box, and then you would probably, I mean, you would have to tell me what then the parameters are. But I know there have been measurements from Alice which try to find something like this.
Yes.
They haven't found it yet, and if these numbers are true, then they should have found it. But it's very, very. I mean, it's 1 in 100 events. That's a lot. Yeah, millions of events that I should have seen. But again,
on the size of the thing.
but I think again, yeah, you're right. I mean, if it is a 6 quark state, then it's kind of, it's not charged, right? It doesn't decay. It might be have much longer lifetime, and then it might not be detectable by the methods they are using.
I was hoping this plot could like constrain.
I don't know if Benjamin has something to say for that. He's the experimentalist.
All what you said is correct. So the assumption from our measurement was that it is a weakly decaying state, and depending on the binding energy of that 6 quark state, it can be something similar to that lambda bound state Jan was calculating, or it is when it's very tightly bound, then it's actually even stable. The prediction of Jeffrey was a stable state.
This is a recent NYU group. I know it's the mass of the Dugard and the radius is really small. I said 2
Okay.
and I was wrong. It's like less than a fraction.
Yeah, then one could probably treat it differently, not like this, but you actually can introduce it like a hadron, right? Like a baryon number 2 hadron, which you can generate differently.
I ask a question about your conclusions at the end, when you have this whatever triple ratio, which depending on the size parameter went flat or had a bump.
Yeah.
So once Alice measures this, and suppose that the data points fall on the orange, what do you conclude?
This one,
Yes.
well, I would conclude that the source radius of the hypertriton is very large.
The source radius.
Yes, that basically the hypertriton at freeze-out can be very far away. The lambda in the hypertriton can be very far away from the deuteron core, basically, when it freezes out.
Okay, that's what you mean by source radius, because usually the source is the fireport, not the system.
No, it's a source of whatever ends up as a hypertriton.
Okay. Good.
And then you could say, is this because it's such a large state? It's because of the wave function, or is it just something with region of homogeneity, or what is it? Okay. Right.
Okay, I think, well, thanks everybody for coming and for today's seminar. And if you want to continue, all of us here are going to Jupiter, downtown. We can meet there at 5:15 or
Soon as possible.
yeah, 5:15.
Oh.
Okay.
So I have to run.
So if any of you online want to join us. Come on. Okay. Bye.
Thank you.
Thank you. Goodbye.
Bye.